Hello! Welcome to another Further Maths video, and I know what you're thinking. Oh my god, what on earth is up with that title? That looks really scary, and I must hold my hands up and say, I'm sorry, it's my fault, because I concentrate sometimes so much on avoiding clickbait titles that I make my titles actually far too detailed to explain exactly what we're doing, but that makes them seem long and scary when actually they're not. So let's not even focus on the title and launch straight into what we're doing, because when you see what we're doing, you'll see that the idea behind what we're doing is not too bad. And then, of course, we'll be looking at the process involved. So, what are we trying to do? We're looking at trig identities, specifically trig identities that involve more than one lot of the variable inside. So, for instance, that could be something like sine of 2 theta or cos of 2 theta. In other words, the double angle identities are examples of what I'm talking about. But they are things we've already seen before. So, what I'm saying is, what happens if we want to progress beyond that? What happens if we have more than 2 theta inside the trig function? What happens if we have, for instance, sine of 3 theta? Well, at this stage, we're still looking at things that you can deal with in Maths A level, because the way you deal with this at Maths A level is you would rewrite it as sine of 2 theta plus theta, in other words, splitting up the 3 theta, because then that allows you to use the compound angle formulas to split that up, and then that would write in terms of sine 2 theta, cos 2 theta, sine theta, cos theta, and then you could use some more identities to rewrite that some even more, and then you'll eventually end up with the answer. And that's great, that works. But then, if we're trying to progress beyond that, well, we start to have a bit of a problem. We can technically do it using our Maths A-level skills, but it's just going to start becoming a real chore to do. For instance, if you want the identity for sine of 6 theta, okay, one way of doing it would be, of course, to rewrite that as sine of 2 lots of 3 theta, which means you can use the double angular identity for sine of 2 theta, but instead of viewing it in terms of sine theta and cos theta, you could view it as being in terms of sine 3 theta and cos 3 theta. In other words, rewriting it as 2 sine 3 theta, cos 3 theta. But then you'd need to use more trig identities to rewrite that, so you'd need to know the trig identity for sine 3 theta and cos 3 theta, which I don't know about you, I don't know off by heart, so I'd therefore have to derive them, so it just starts becoming really long to do. You could alternatively view it as sine of 5 theta plus theta, using a similar strategy to what we use for sine of 3 theta, but again, that's going to take a really long time, because then you need the identity for sine of 5 theta, and if you want to split that up, that's then going to take even more effort. Or even just using purely double angle identities, but then you're just plugging double angle identities into double angle identities into double angle identities, and okay, that's also going to take quite a while. So, if you want to find an identity for sine of 6 theta, you shouldn't really do any of those things because it's too much effort. So, that's what leads me on to what we're doing today. We're basically trying to find the identities for these functions if there's higher numbers of thetas inside, without having to just use 500 different trig identities in order to be able to do it. So, what do you need to know in order to be able to do it? Well, you need these key facts. You need to know that cos of n theta is equal to the real component of the complex number cos of n theta plus I sine of n theta. And then similarly, sine of n theta is just the imaginary component of that same complex number. Now that might seem weird already, because we're introducing complex numbers to help us find trig identities for trig functions that we were already doing with in Maths A level quite fine without involving complex numbers ever. So why are we now making things seem more scary? Well, let's look at an example, because I must admit this stuff is much easier to just show through doing an example and then generalizing after that, rather than trying to just tell you the steps beforehand. And the example we're going to be looking at in this video is the identity for sine of 6 theta. There you go. See, I hinted at that earlier in the video, that that's what we'll be looking at, and I don't like to leave you hanging. This is the identity for sine of 6 theta. Now, interestingly, the wording for this question does give us a few clues as to how we're going to approach it. The first key point is the fact it mentions that we have to use de Moivre's theorem. And the fact it's been very specific like that is important, because it implies that A, we're going to be using de Moivre's theorem, so it's a nice clue as to what we're going to be doing, but also it makes it clear that even if you wanted to use the method where you plug double angle identities into other double angle identities into other double angle identities, you wouldn't be allowed to do it that way if you wanted to get the marks. But admittedly, I'm not sure why you'd want to do it that way, because that way is a bit of a chore. But also the other key important point is it is a prove that question, which is important because, as always, for prove that question, it means we have to make sure we're showing enough working, not skipping steps, etc, etc. So with that said, let's get on with it. The first thing you need to do is you need to use the key fact we just mentioned. You need to realize that sine of 6 theta can be rewritten as the imaginary component of cos of 6 theta plus I sine of 6 theta. Cool. And what that's allowed us to do is it now means we've got a bigger expression to work with, which means we have more things to manipulate and rewrite, and so therefore it'll make us easier for us to be able to get the other stuff we're trying to prove on the right hand side. But for the moment, I'm just going to focus on the cos of 6 theta plus I sine of 6 theta part, and that's just because for the moment I can't be bothered to write the imaginary component notation every single time. But just bear in mind, of course, the imaginary component notation means ultimately when we do rewrite cos 6 theta plus I sine 6 theta, the imaginary number parts of that expression and all its rewritings are going to be the parts that are related to sine of 6 theta. So, therefore, how are we going to rewrite cos 6 theta plus I sine of 6 theta? Well, the clue was in the question. We're going to use the Moivre's theorem. Because this is, of course, of that format, so we can rewrite it as cos of theta plus I sine of theta, but taken to the power of 6, because the Moivre's theorem allows us to take a numbered multiple of theta inside the two trig functions, as long as it's the same multiple in both of them, and move it outside as a power. And that's great because it means we've got some brackets that we can work with, and I know what you're thinking, oh my god, do you really expect us to multiply out those brackets? And I'm afraid the answer is actually yes. And that's going to sound quite scary and probably makes you question if this method actually is quicker. Well, it all depends on how quick you are at doing binomial expansion. If you're not quick at doing binomial expansion, yes, this is going to take you a while, but therefore it's motivation to get quick at doing binomial expansion because ultimately you're meant to know how to do that anyway for Maths A level, and therefore it's in your interest to be able to do it quickly and accurately. But therefore, as we're now reusing it for this stuff, double the reason to get good at it. And actually, if you do get good at it, it is quicker than doing all the double angle identity plugging into itself sort of method, because ultimately binomial expansion doesn't take that much thinking when you get good at it because it's very algorithmic in its approach. You're just doing the same process to lots of different things, whereas the problem is with the other method of plugging trig identities into other trig identities, you are having to concentrate very carefully on what's being plugged into what and what's getting multiplied by what. So yes, it doesn't seem quicker, but trust me, it is quicker. So therefore, to prove the point, I'm just going to do this binomial expansion fairly quickly. It's just NCR parts, so we'll start with 6C0, which is just 1, and then multiply by one of the things, so let's say the I sine theta to the power of 0, and then multiply by the other thing to the rest of the power that's not been used yet. So as we did I sine theta to the power of 0, that means the whole power of 6 has to be applied to the cos. We'll do 6C1, which is 6, times by I sine theta, times by cos to the power of 5 theta, 6c2, which is 15, I squared, sine squared theta, that means we've got a power of 4 remaining to apply to the other thing, and continuing on. You'll notice as I'm writing this stuff that I am bothering to write out the I being taken to the various powers, and that's because, well, two reasons. First of all, it's to show that question's already mentioned, I'm not wanting to skip steps, but also it helps me avoid silly mistakes. As I'm just rewriting out, I'm just working through the method. This doesn't take that much thought at the moment. I'm just working through it, and what will happen to the I's will get sorted out eventually, and therefore for the moment I don't have to worry about doing it. So we do eventually end up with all of this stuff. And yes, I did genuinely do that at that speed. Arguably, I'd do it more quickly if I wasn't talking. And that's the sort of level you want to get to with binomial expansion, just realizing the sort of pattern that goes along, and obviously using a calculator to work out the NCR coefficients. So this stuff really isn't that long if you do get quick at doing binomial expansion. Now, the thing to be aware of is we are trying to find specifically sine of 6 theta. And that's important because that means we want just the imaginary component of that expression we just looked at, which is obvious to see for the first two terms. We know cos to the power of 6 theta is real, so we're not interested in that. And then 6I sine theta cos of 5, or cos to the power of 5 theta I should say, is the one we're interested in because it's got an imaginary number involved. But worth pointing out straight away, if we're taking the imaginary component, you don't include the I once you've taken the imaginary component. Taking the imaginary component just means what's effectively the coefficient of the imaginary number I. So therefore, I'm just going to write 6 sine theta cos to the power of 5 theta. But then there are some other things as well. And the thing to bear in mind is just being aware of what you could call the I cycle, I guess, which is, I squared is equal to -1, and I cubed is equal to -I, and I to the 4 is equal to +1 again. And just being aware, therefore, as you progress through the powers of I, it's just fluctuating between real and imaginary numbers. So therefore 15I squared is a real number, so we're going to ignore that term. 20I cubed is an imaginary number, so we're interested in this term. And the other interesting aspect to this, not only is in this expression you've got that fluctuation between real, imaginary, real, imaginary, real, imaginary. So by the way, 6I to the power of 5 term is going to be imaginary as well. But the other thing that's fluctuating is also within the imaginary terms in comparison to each other. And the same effect happens in comparison to the real terms to each other. You've also got a plus minus situation going on. So therefore, again, actually there's huge aspects to this that can help you speed up just because you know what you're expecting to get. You don't actually have to do proper calculations. You already know you're expecting the first term of the imaginary component to be a positive thing, the second term to be a negative thing. So this just helps add a lot of time savings to what we're doing because you already know, okay, I'm only picking half the terms in the full expansion that I did above, and then of those terms, half of those are going to be positive and half of them are going to be negative. So, as I said, this stuff really isn't as bad as it first appears. And ultimately, at this stage, we've already got a completely valid trig identity for sinus 6 theta. So if you were just trying to do this for your own benefit rather than a question that's asked of you, then technically, hooray, we've already found a trig identity for sinus 6 theta. That doesn't take that much working to do in reality. The only thing to be aware of after that, though, is we've got a prove it question, so therefore we're aware that this is not what the question wanted us to end with, so therefore that's the only reason we're having to continue. But the advantage of that is we do have a clue as to what we need to do in order to continue writing it. For instance, we can see they've got a 2 cos theta factored out the front, so therefore actually that's the first thing we could do. We could factorize 2 cos theta out of our expression, so continuing on we could do that next. But the other thing to bear in mind is we notice that's the only place cos theta appears in the expression they've got. The rest of it is all in terms of sine theta. So once we've factorized 2 cos theta out of the entire expression, we know we're going to have to be converting any remaining cos thetas to sine thetas. So doing that, we can factorize that 2 cos theta out as promised. So therefore, we're going to be left with 3, dividing the 6 by 2, and then dividing the cos to the 5 theta by cos theta will leave us with a cos to the power of 4 theta inside the brackets, and we'll end up with a minus 10 of cos squared theta, sine cubed theta, and then lastly plus 3 sine to the 5 theta. There you go. Cool, so all we've got to do now is actually ultimately just maths A-level stuff. Admittedly, at this point onwards, we're not doing any further maths content at all, but we just have to do this stuff anyway to finish off the question. So we want to replace all these remaining cos theta expressions that are appearing inside the brackets, because those are the ones that weren't appearing in the thing we were trying to aim for. So in order to do that, you need to make use of the identity sine squared theta plus cos squared theta equals 1, because that allows you to replace powers of cos theta in terms of powers of sine theta. And conveniently, and this isn't a coincidence, you'll notice that we've got an even power of cos theta in all the places it's appearing that we need to replace it for. Because that means, of course, the cos squared theta immediately, we can just replace that with 1 minus sine squared theta. But cos to the power of 4 theta, do be aware that's secretly cos squared theta squared. Power of 4 is something squared, then squared again. So therefore, that could be replaced with 1 minus sine squared theta, and then it's being squared by the brackets. So therefore, our expression is going to be 2 cos theta, lots of 3, lots of 1 minus sine squared theta, all squared, times by sine theta. Then we have minus 10, 1 minus sine squared theta, lots of sine cubed theta, and then we've got the plus 3 sine to the power of 5 theta. Now this part is the most tedious part of the question because it is just now multiplying out a load of brackets. But hey, whatever. It's marks. You do get given the time to do it in the exam. Just be really careful when you're doing it. And actually, once again, worth bearing in mind, you can use your knowledge of binomial expansion to actually help you do this more quickly, because the 1 minus sine squared all squared theta, well, that's just a mini binomial expansion itself. We're going to have, technically 2c0 lots of 1 squared minus, plus 2 lots of the 1 times the minus sine squared theta, so that's minus 2 sine squared theta, and then plus the minus sine squared theta all squared, which is positive sine to the 4 theta. So, this stuff doesn't take too much thought if you're careful. Another thing to be aware of is we're multiplying by lots of things out here. So if necessary, do the multiplying brackets in more than one stage like I've done here. I first concentrate on doing the power of 2 applied to those brackets, and then I'm separately going to multiply it out by the 3 sine theta later. But then we're doing minus 10 sine cubed theta times by the stuff inside those brackets. That'll be a minus 10 sine cubed theta. And then we have minus times a minus, which are positive. We've got a 10, and then we're going to have a sine to the power of 5 theta there. And then we've still got that 3 sine to the 5 theta on the end. And then continuing on. So therefore, we are going to have 3 sine theta. We are going to have minus 6 sine to the power of 3 theta. And then we're going to have plus 3 sine to the power of 5 theta. Worth pointing out, again, to help you avoid silly mistakes, you're looking for patterns here, and something that helps me spot whether I made a silly mistake or not. I'm noticing there's still that sort of gap of a power of 2 in between each of these first 3 terms. So when doing lots of multiplying brackets, there's always things you can do to check if you've made some very silly errors as you go along. And the rest has stayed the same. And actually, the last bit of advice I can give you after this is we're now at the end trying to gather all our terms together. A mistake some students make is, as they're trying to gather the terms together to keep track of what they have or haven't dealt with, they start crossing terms out, which you shouldn't do, because ultimately we want the examiner to be able to see our lines are working because it's part of the method. So instead, if you do want to still be able to keep track of what you have or haven't dealt with, instead of actually literally crossing out the things that we've written, do a little tick like below all the bits of lines are working, because then you can still have this idea of keeping track of what you have or haven't combined yet without literally crossing it out, which means the examiner can't see it. So for instance, I am going to write this as, of course, we've got a 3 sine theta, and that's the only sine theta, so therefore that's done. We've then got a minus 6 sine cubed and a minus 10 sine cubed, so that means we've got minus 16 sine cubed theta. And then lastly, we've got the 3 sine to the 5, 10 sine to the 5, so that's 13, plus another 3 is plus 16 sine to the 5 theta. And there you go. We have proven it as required. As it's just a trig identity proof, I don't feel under pressure to have a more formal conclusion than that, because it's kind of clear that I've reached what we wanted to prove, because it looks exactly the same as what we're trying to prove. But there you go, that's how you can use de Moivre's theorem to prove some trig identities. One little side note that some students find helpful to speed up the process of writing all this stuff out. Some students like to say, let c equal cos theta at the very beginning of these questions and let s equal sine theta, because that means instead of having to write sine and cos every single line of these workings, you can just write powers of c and powers of s if you want. I personally didn't do that and personally don't do that, because although it takes longer to write out sine and cos, I don't trust myself enough to be able to write the letter S without it looking like the number 5, and therefore I know I'm going to make a silly mistake if I do that. So it's all about knowing yourself and knowing what you would be able to do without making silly mistakes. But anyway, that will do us for today. Hopefully you found today's video useful, and I'll see you in a future video.